What if two tiny silicon chips changed human civilization forever? It sounds almost impossible. After all, they were no larger than a fingernail, contained only a few thousand transistors, and possessed computing power so limited that a modern digital wristwatch could outperform them millions of times over. Yet these humble inventions became the foundation upon which the modern digital age was built. Every powerful gaming computer, rendering breathtaking virtual worlds. Every artificial intelligence system answering complex questions in seconds. Every cloud server processing billions of requests each day. Every smartphone connecting people across continents. And every laptop helping students, scientists, engineers, and artists create the future can trace its technological ancestry back to two remarkable inventions created just 1 year apart. Their names were the Intel 4004 and the Intel 8008. Today, we live in a world surrounded by computing. Artificial intelligence can generate images, summarize research, translate languages, assist doctors in diagnosing diseases, and even help engineers design the next generation of spacecraft. Modern processors contain tens of billions of transistors operating at clock speeds measured in gigahertz, performing trillions of operations every second while consuming surprisingly little power. They power autonomous vehicles navigating busy streets, satellites orbiting Earth, industrial robots assembling automobiles with astonishing precision, and scientific supercomputers modeling the climate, exploring the origins of the universe, and searching for new medicines. These extraordinary machines appear so advanced that it is easy to forget their humble beginnings. The story begins not with sleek laptops or smartphones, but with a period when computers were enormous, expensive, and inaccessible to almost everyone. Computing was once reserved for governments, universities, military organizations, and the largest corporations. Machines occupied entire rooms, required teams of specialists to operate, and cost fortunes to purchase and maintain. Ordinary people could admire computers from afar, but the idea of owning one at home seemed almost as unrealistic as owning a personal rocket ship. During the late 1960s, the electronics industry stood at a crossroads. Integrated circuits had already begun replacing individual transistors, making electronic devices smaller and more reliable. Engineers recognized that each new generation of semiconductor technology could place more components onto a single chip of silicon. The question was no longer whether electronics could continue shrinking, but how far that trend could go. Few imagined that an entire central processing unit, the electronic brain of a computer, could someday fit onto a single integrated circuit. For decades, the central processor of a computer had been constructed from numerous separate chips and circuit boards working together. Arithmetic operations, control logic, registers, memory interfaces, and input-output functions occupied different sections of large electronic systems. Building a computer required assembling hundreds or even thousands of components into carefully engineered architectures. Complexity translated directly into higher costs, greater power consumption, larger physical size, and increased opportunities for failure. Computers were impressive achievements of engineering, but they remained inaccessible to ordinary consumers because they were simply too large and too expensive. And then, an unexpected opportunity emerged from a seemingly ordinary business project. A Japanese calculator manufacturer sought a more efficient electronic design for its programmable calculators. What appeared to be a routine commercial contract would soon evolve into one of the most significant engineering breakthroughs in history. Instead of designing many specialized chips dedicated to individual calculator functions, a small group of visionary engineers began exploring a radical alternative, a single, programmable chip capable of performing many different tasks simply by changing its instructions. That concept represented a profound shift in thinking. Rather than building hardware specifically for one machine, engineers could create a general-purpose processor whose behavior depended on software. A single chip could become the flexible heart of countless electronic devices. This idea would eventually transform not only calculators, but also computers, industrial equipment, medical instruments, communication systems, automobiles, spacecraft, and nearly every digital technology developed afterward. The first realization of that revolutionary concept arrived in 1971 with the Intel 4004. Modest by today's standards, it was a 4-bit microprocessor containing approximately 2,300 transistors and operating at a clock frequency of up to 740 kilohertz. It could execute roughly 92,000 instructions per second, figures that now seem almost unimaginably small. Yet its true significance lay not in its raw performance, but in its architecture. For the first time, the essential functions of a central processing unit had been successfully integrated onto a single commercially available chip. Just 1 year later, Intel introduced another remarkable innovation, known as the Intel 8008. This new processor expanded the vision dramatically. It moved from a 4-bit architecture to an 8-bit design, increasing computational capability, memory addressing, and flexibility. With approximately 3 512 transistors and support for up to 16 kilobytes of memory, it represented an important step toward creating practical general-purpose computers built around a single microprocessor. Although still primitive, compared with later generations, it demonstrated that the microprocessor was not merely a clever solution for calculators, but the beginning of an entirely new era in computing. The Intel 4004 and Intel 8008 are often remembered simply as early processors, but their historical importance extends far beyond technical specifications. Together, they introduced a new philosophy of computer engineering. They proved that computing power could become smaller, cheaper, more reliable, and more widely available. They shifted the industry away from constructing processors, from dozens of interconnected chips toward integrating intelligence into a single piece of silicon. This breakthrough reduced costs, simplified design, encouraged experimentation, and opened the door to innovations that previously seemed impossible. From these pioneering chips emerged an extraordinary chain of technological progress. More powerful processors followed, enabling hobbyist computers, business systems, personal computers, graphical interfaces, the internet, mobile devices, cloud computing, and ultimately artificial intelligence. Every generation built upon the engineering lessons learned from those first microprocessors. Their influence echoes through every modern CPU, GPU, AI accelerator, and system-on-chip produced today. This is the true story of how two tiny pieces of silicon, introduced in 1971 and 1972, ignited the personal computer revolution and forever changed the future of computing, setting humanity on a path toward the interconnected digital civilization we now call everyday life. Before the dawn of the microprocessor, the world of computing looked radically different from the one we know today. Computers already existed, but they were rare, expensive, and unimaginably large. They were not machines that sat on a desk or fit inside a backpack. Instead, they occupied entire rooms filled with rows of metal cabinets, bundles of cables, cooling equipment, and flashing indicator lights. Entering a computer room often felt like stepping into an industrial facility rather than an office. Only highly trained operators could interact with these machines, and every minute of computing time carried significant value. For governments, universities, research laboratories, banks, and major corporations, computers were powerful tools. For ordinary people, they remained distant technological marvels. The evolution toward these machines had taken decades. Early electronic computers of the 1940s relied on thousands of vacuum tubes, consuming enormous amounts of electricity while generating tremendous heat. They required constant maintenance because individual tubes failed frequently. Despite these limitations, they demonstrated that electronic computation could solve mathematical problems at speeds impossible for humans. As transistors replaced vacuum tubes during the 1950s, computers became more reliable, somewhat smaller, and more energy efficient. Integrated circuits introduced in the 1960s represented another major leap, allowing multiple transistors to be fabricated on a single silicon chip. Each technological breakthrough made computers faster, cheaper, and more dependable, but the central processor itself remained a complex collection of many separate integrated circuits working together. A typical computer processor before 1971 was not a single component, but an intricate system assembled from numerous specialized chips mounted across multiple printed circuit boards. One group of circuits handled arithmetic calculations. Another controlled instruction sequencing. Additional chips managed registers, timing, memory access, and communication with input and output devices. Engineers designing a computer had to ensure that every one of these components operated in perfect synchronization. The result was powerful, but expensive hardware that demanded careful engineering and substantial manufacturing resources. This complexity created a significant barrier to widespread computing. Even relatively modest computers required hundreds of integrated circuits and thousands of individual electronic connections. Manufacturing costs remained high. Assembly required skilled technicians, and troubleshooting hardware failures could consume countless hours. Every additional circuit board increased the chances of defects, electrical noise, and reliability problems. As a consequence, computers remained products for institutions rather than individuals. Mainframe computers represented the pinnacle of this era. Companies such as IBM produced systems capable of processing payroll, scientific calculations, census data, airline reservations, and financial transactions on an unprecedented scale. These machines served hundreds or even thousands of users through terminals connected over dedicated communication lines. Organizations invested millions of dollars in acquiring, maintaining, and operating them. Specialized air conditioning systems controlled temperature and humidity to protect delicate electronics. Teams of programmers, operators, and maintenance engineers kept these installations running around the clock. Alongside the mainframe emerged the mini-computer. Introduced during the 1960s by companies including Digital Equipment Corporation, mini computers dramatically reduced both size and cost compared with traditional mainframes. Although still far too expensive for personal ownership, they made computing accessible to smaller businesses, universities, engineering firms, and laboratories. Machines, such as the PDP series, demonstrated that useful computing power could fit inside a few cabinets rather than an entire room. Even so, these systems still depended on processors assembled from many separate integrated circuits rather than a single microprocessor. For ordinary families, the concept of owning a computer remained almost unimaginable. Consumer electronics of the late 1960s consisted primarily of televisions, radios, stereos, and simple electronic calculators. Household appliances were becoming more sophisticated, but they contained little or no programmable intelligence. Automobiles relied almost entirely on mechanical systems. Telephones were purely analog communication devices. Cameras used film instead of digital sensors. The digital revolution had not yet reached everyday life. Engineers understood that integrated circuits were improving rapidly. Gordon Moore, one of Intel's future founders, had famously observed in 1965 that the number of components on integrated circuits appeared to double at regular intervals while manufacturing costs declined. This observation, later known as Moore's Law, suggested an extraordinary future for semiconductor technology. If chip density continued increasing, increasingly complex electronic systems might someday fit onto remarkably small pieces of silicon. At the time, however, few believed that an entire central processing unit could be compressed onto a single integrated circuit. While the computer industry pursued larger and more capable systems, another field quietly expanded the demand for compact electronics. Electronic calculators were replacing mechanical calculating machines in offices and businesses around the world. Manufacturers competed to build calculators that were smaller, faster, more reliable, and less expensive. Designing these products required numerous custom integrated circuits dedicated to specific mathematical operations and control functions. Every new calculator model often demanded an entirely new collection of specialized chips, making development expensive and inflexible. This environment created an opportunity for innovation. If one programmable chip could replace several dedicated logic circuits, manufacturers could simplify production while creating more versatile products. A programmable processor could perform many different tasks simply by executing different instructions stored in memory. Instead of redesigning hardware for every new product, engineers could modify software while keeping much of the hardware unchanged. Such an approach promised lower costs, faster development, and unprecedented flexibility. At the center of this opportunity stood a young company founded only a few years earlier. In July 1968, semiconductor pioneers Robert Noyce and Gordon Moore, joined by Andrew Grove and several other talented engineers, established Intel, short for Integrated Electronics. Unlike established computer manufacturers, Intel did not initially set out to build complete computers. Its primary focus was semiconductor memory. The founders believed that advances in silicon technology would revolutionize the production of memory chips, replacing older magnetic core memory with faster, denser, and more reliable semiconductor alternatives. The company's early years were defined by ambition, technical excellence, and relentless experimentation. Intel attracted engineers eager to push the boundaries of semiconductor manufacturing. Working in California's rapidly growing Silicon Valley, the company embraced a culture that valued innovation, practical problem solving, and bold engineering decisions. Resources were limited, competition was fierce, and success was far from guaranteed. Every contract mattered, and every technical breakthrough could determine the company's future. Intel's first successful products were memory chips rather than processors. Devices such as the 3101 Schottky bipolar RAM and later semiconductor memory products established the company's reputation for advanced chip design. These achievements generated revenue while demonstrating Intel's expertise in integrated circuit fabrication. More importantly, they provided valuable experience in manufacturing increasingly sophisticated silicon devices with high reliability and competitive yields. Yet beneath its success in memory technology lay a broader vision. Intel's engineers recognized that silicon-integrated circuits could accomplish far more than storing data. As fabrication techniques improved, it became possible to integrate ever more complex logic onto individual chips. The challenge was determining which electronic systems would benefit most from this rapidly expanding capability. No one yet knew that a calculator project from Japan would soon provide the perfect opportunity to answer that question. By the end of the 1960s, all the essential ingredients for a technological revolution were quietly coming together. Semiconductor manufacturing had matured enough to support increasingly complex chips. Integrated circuits were becoming more affordable each year. Visionary engineers were beginning to rethink traditional computer architecture. A young company with exceptional semiconductor expertise was searching for opportunities beyond memory. The world still relied on room-sized computers assembled from countless individual components, but the possibility of placing an entire central processing unit onto a single silicon chip was no longer merely a dream. It was rapidly becoming an engineering challenge, waiting for the right people, the right idea, and the right moment in history. The story of the Intel 404 began not with a grand plan to revolutionize computing, but with a request to build a better calculator. In the late 1960s, electronic calculators were becoming increasingly popular in businesses and engineering offices around the world. They were replacing bulky mechanical adding machines and offering users faster, more reliable calculations. Competition among manufacturers was fierce, and companies sought new ways to make their products smaller, more capable, and less expensive. One of those companies, the Japanese calculator manufacturer Busicom, unknowingly set in motion one of the greatest technological revolutions in history. Busicom wanted to develop an advanced family of programmable calculators that could outperform existing products. Its engineers envisioned machines capable of handling a variety of mathematical functions while remaining compact enough for commercial use. The original design called for a collection of specialized integrated circuits, each dedicated to performing a specific task. Separate chips would manage arithmetic operations, keyboard input, display control, memory, timing, and program execution. This approach reflected the standard engineering philosophy of the time. Every function had its own hardware, and increasing functionality usually meant adding even more custom chips. To turn this ambitious design into reality, Busicom partnered with Intel, a young American semiconductor company that had built a growing reputation for producing advanced memory chips. Intel had only been founded in 1968, and while it possessed exceptional expertise in semiconductor fabrication, it had little experience designing complete processor systems. Nevertheless, the opportunity represented an important commercial contract, and Intel assigned several talented engineers to evaluate the project. Among them was Ted Hoff, an engineer with a remarkable ability to think beyond conventional solutions. After reviewing Busicom's proposed architecture, Hoff recognized a fundamental problem. The calculator required too many custom integrated circuits, making the design both expensive and difficult to manufacture. Every additional chip increased production costs, complicated assembly, and reduced overall reliability. Hoff believed there had to be a more elegant approach. Rather than building a separate chip for every individual calculator function, Hoff proposed something radically different. Instead of fixed function hardware, he imagined a single programmable processing unit capable of executing instructions stored in memory. The processor would perform different operations simply by following software commands rather than relying entirely on dedicated electronic circuits. Such an architecture would dramatically reduce the number of required chips while making the system far more flexible. Although the processor would initially be used in calculators, the same fundamental design could potentially control many different electronic devices simply by changing the program. This idea represented a revolutionary departure from accepted engineering practice. Computers already use programmable processors, but those processors were assembled from numerous integrated circuits distributed across multiple circuit boards. Hoff's concept suggested integrating the essential functions of a central processing unit onto one chip. It was an extraordinarily ambitious vision, especially considering the manufacturing limitations of the late 1960s. Turning that vision into working silicon required another extraordinary engineer. Federico Faggin joined Intel in 1970 after developing groundbreaking Silicon Gate MOS technology while working at Fairchild Semiconductor. Silicon Gate technology offered major advantages over earlier manufacturing methods. It enabled smaller transistors, higher operating speeds, improved reliability, and greater transistor density on each chip. Without these manufacturing advances, placing an entire processor onto one integrated circuit would likely have remained impractical. Intel assigned Faggin to lead the implementation of the new processor architecture. While Hoff had developed the architectural concept, Faggin transformed that vision into a manufacturable semiconductor design. He created the detailed logic, transistor layouts, circuit timing, testing methodology, and production processes necessary to bring the processor into existence. His work demanded both creativity and precision, as no one had previously built a commercial microprocessor of this kind. Another key contributor was Stanley Mazor, who worked closely with Hoff in refining the processor's architecture and instruction set. Mazor helped develop many of the programming concepts that would allow software to control the processor efficiently. Together, Hoff and Mazor established the logical framework that defined how instructions would be executed, how data would move within the processor, and how programmers would interact with the new device. Meanwhile, Masatoshi Shima, an engineer from Busicom, played a vital role throughout the project. Shima possessed deep knowledge of the calculator's functional requirements and collaborated extensively with Intel's engineering team. His understanding of the intended applications helped shape many implementation details, ensuring that the new processor could successfully meet Busicom's commercial objectives. Rather than simply handing Intel a specification and waiting for results, Shima became an active engineering partner whose contributions proved essential to the project's success. Despite the brilliance of the team, enormous technical challenges remained. Integrating an entire central processor onto one chip had never been attempted on a commercial scale. Every transistor consumed valuable silicon area. Every circuit required careful optimization to balance its speed, power consumption, and manufacturability. Designers had to minimize complexity while ensuring reliable operation across thousands of manufactured chips. Errors that might be corrected easily in modern computer-aided design systems often had to be identified through painstaking manual analysis and testing. The available semiconductor fabrication technology imposed additional constraints. Manufacturing yields were relatively low by modern standards, meaning that even minor design flaws could render large numbers of chips unusable. Engineers continuously refined layouts, adjusted manufacturing parameters, and improved testing procedures to maximize production quality. Faggin introduced innovative design methodologies that significantly improved both performance and manufacturing efficiency, helping transform a theoretical concept into a practical commercial product. After months of intensive engineering, Intel completed the processor along with several supporting integrated circuits that formed the MCS4 chipset. The processor itself became known as the Intel 4004. Officially introduced in November 1971, it represented something the electronics industry had never seen before, a commercially available microprocessor integrating the essential functions of a central processing unit onto a single silicon chip. By modern standards, its specifications appear modest, yet they were extraordinary for their time. The Intel 4004 was a 4-bit processor capable of processing 4 bits of data simultaneously. It contained approximately 2,300 transistors fabricated using silicon gate PMOS technology. The processor operated at clock frequencies up to 740 kHz and could execute approximately 92,000 instructions per second under ideal conditions. It supported a sophisticated instruction set for arithmetic operations, branching, memory manipulation, and input-output control, making it remarkably versatile despite its small size. Although designed initially for calculators, the Intel 4004 demonstrated capabilities extending far beyond simple arithmetic. Because it was programmable, the same processor could control industrial equipment, traffic systems, laboratory instruments, vending machines, medical devices, and countless other electronic applications by running different software. This flexibility distinguished it from previous fixed-function integrated circuits and hinted at an entirely new future for electronics. The significance of the Intel 4004 cannot be measured solely by transistor count or processing speed. Its greatest achievement was conceptual. It proved that an entire programmable CPU could exist on one integrated circuit and function reliably in commercial products. This dramatically reduced hardware complexity while opening possibilities that engineers had scarcely imagined only a few years earlier. Instead of designing unique logic for every electronic device, manufacturers could increasingly rely on programmable processors, allowing software to define functionality rather than dedicated hardware alone. Initially, many observers viewed the Intel 4004 simply as an innovative calculator component. Few recognized that they were witnessing the birth of a technological revolution. Yet within that tiny piece of silicon lay a new philosophy of computing, one that would eventually reshape industries, enable personal computers, connect billions of people through digital networks, and form the foundation of the information age. The world's first commercial microprocessor had arrived, and although its immediate applications seemed modest, its long-term impact would extend further than even its creators could have imagined. The introduction of the Intel 4004 in late 1971 marked a historic milestone in electronics. For the first time, a commercially available central processing unit existed on a single silicon chip, proving that an idea once considered almost impossible could become a practical reality. Engineers around the world recognized the elegance of its architecture, while manufacturers began exploring applications far beyond the programmable calculators for which it had originally been designed. Yet, as revolutionary as the Intel 4004 was, it also revealed the limitations of first-generation microprocessor technology. Every breakthrough exposes new possibilities, and every possibility eventually uncovers new challenges. The success of the 4004 quickly made one thing clear. If microprocessors were to move beyond specialized embedded applications and become the heart of future computers, they would need to become significantly more capable. The Intel 4004's greatest strength was its simplicity. By integrating the essential functions of a central processing unit onto one integrated circuit, it dramatically reduced the number of components required to build intelligent electronic systems. Designs that previously required multiple circuit boards filled with dedicated logic chips could now be simplified into far more compact and reliable products. Manufacturers benefited from lower component counts, easier assembly, improved reliability, and reduced production costs. But these advantages alone made the microprocessor one of the most important semiconductor innovations of its era. Another remarkable strength was programmability. Before the arrival of the 4004, many electronic products relied on fixed hardware logic. If manufacturers wanted a device to perform a different task, they often had to redesign the electronics themselves. The Intel 4004 introduced a more flexible philosophy. Instead of changing hardware, engineers could modify software instructions stored in memory. One processor could serve many different purposes simply by executing different programs. This concept fundamentally changed electronic system design and became one of the defining characteristics of modern computing. The processor also demonstrated impressive reliability for its time. Reducing hundreds of individual electrical connections into a single integrated circuit minimized many potential points of failure. Fewer chips meant fewer solder joints, fewer wiring errors, and fewer opportunities for electrical faults. In industrial environments where reliability directly affected productivity and maintenance costs, this represented a major advantage. Manufacturers quickly realized that programmable microprocessors could make electronic control systems both simpler and more dependable. The Intel 4004 also consumed relatively little power compared with larger processor assemblies built from numerous integrated circuits. Although modern low-power processors are vastly more efficient, the reduction in hardware complexity achieved by the 4004 made it attractive for compact electronic products, where space and power consumption mattered. Its small physical size opened possibilities for devices that would have been impractical using traditional processor designs. Despite these achievements, the Intel 4004 remained a product of the technological constraints of its time. Its 4-bit architecture reflected its original purpose as the controller for programmable calculators. Processing 4 bits of information at a time worked well for decimal arithmetic and relatively simple control tasks, but it imposed significant limitations on broader computing applications. As engineers began imagining more sophisticated systems, the processor's restricted data width quickly became apparent. One of the most important limitations involved memory. The Intel 4004 could address only a relatively small amount of program and data memory. For calculator applications, this capacity was entirely sufficient. Calculator programs were compact, repetitive, and highly specialized. More general computing tasks, however, required increasingly larger software programs, additional variables, and more extensive data storage. Engineers soon discovered that the available address space limited the complexity of applications the processor could realistically support. Its instruction set, while innovative, also reflected its specialized origins. The Intel 4004 included operations optimized for calculator functions, numerical processing, and straightforward control logic. Although programmers demonstrated remarkable creativity in using the processor for many unexpected purposes, more demanding applications required richer instruction sets capable of handling increasingly sophisticated computational tasks. As software grew more ambitious, designers recognized the need for processors with expanded capabilities and greater programming flexibility. Performance presented another challenge. Operating at clock speeds up to approximately 740 kilohertz and executing around 92,000 instructions per second. The Intel 4004 represented an extraordinary achievement for 1971, yet these specifications also defined practical limits. Simple embedded control systems performed well, but applications involving substantial calculations, complex decision-making, or larger software programs quickly reached the processor's performance boundaries. As expectations for programmable electronics increased, greater computational power became increasingly desirable. The processor's architecture further reflected the design priorities of its original calculator project. Every engineering decision involved balancing transistor count, manufacturing complexity, silicon area, and production cost. With approximately 2,300 transistors available, designers carefully optimized every circuit to deliver essential functionality while remaining manufacturable. This necessity meant sacrificing features that would later become valuable for more advanced computing systems. The Intel 4004 was not intended to become the universal processor for every application. It was designed to solve a specific engineering challenge, and it accomplished that goal brilliantly. Nevertheless, engineers soon began adapting the microprocessor for uses its creators had never fully anticipated. Industrial automation emerged as one of the earliest areas of adoption. Factories required programmable controllers capable of monitoring sensors, operating machinery, and coordinating manufacturing processes. Replacing complex assemblies of dedicated logic circuits with a programmable microprocessor simplified system design while allowing manufacturers to modify production equipment through software updates rather than complete hardware redesigns. The Intel 4004 also found applications in scientific instruments, medical equipment, traffic control systems, cash registers, vending machines, and communication devices. Each successful implementation demonstrated the remarkable flexibility of programmable microprocessors. Instead of designing unique electronics for every product, manufacturers increasingly viewed software as the key to product differentiation. This represented a profound shift in engineering philosophy that would influence virtually every electronic industry in the decades ahead. Yet every new application also highlighted additional limitations. Engineers developing more advanced terminals, controllers, and computer-like systems wanted processors capable of handling larger amounts of data, supporting more memory, and executing more sophisticated software. 4-bit processing increasingly appeared too restrictive for the expanding ambitions of computer designers. The demand was no longer simply for a programmable calculator controller. The industry was beginning to envision genuine general-purpose microcomputers. Inside Intel, these developments did not go unnoticed. Company engineers understood that the Intel 4004 had successfully demonstrated the feasibility of the microprocessor concept, but they also recognized that it represented only the first step of a much longer technological journey. Semiconductor manufacturing technology continued improving rapidly. More transistors could now be placed onto individual chips, allowing architects greater freedom to expand processor capabilities. The challenge was no longer proving that a CPU could fit onto one chip. The challenge had become determining how powerful that chip could become. At the same time, opportunities beyond calculators were beginning to emerge. Businesses sought more capable computer terminals. Industrial customers requested increasingly sophisticated programmable controllers. Engineers envisioned compact computer systems that could perform tasks once reserved for much larger mini-computers. These new markets demanded processors with wider data paths, expanded instruction sets, larger address spaces, and greater overall computational capability. The lessons learned from the Intel 4004 proved invaluable. Its architecture demonstrated the practicality of integrating a central processing unit onto a single silicon chip. Its commercial success validated the programmable processor concept. Its limitations provided a clear roadmap for future improvements. Rather than representing the final destination, the Intel 4004 became the foundation upon which more advanced microprocessors would be built. Intel's engineers now faced an exciting opportunity. They had shown the world that the microprocessor was possible. The next challenge was to show that it could become the heart of real computer systems, rather than merely an intelligent controller. Achieving that vision would require moving beyond the boundaries of 4-bit processing toward a new generation of microprocessors with significantly greater capability. Within a year of the Intel 4004's introduction, the next step was already taking shape. It would arrive in the form of a processor that expanded nearly every aspect of its predecessor's design, pushing the young field of microprocessor engineering closer to the personal computer revolution that was still waiting just beyond the horizon. The remarkable success of the Intel 4004 proved that a complete central processing unit could be integrated onto a single silicon chip. It demonstrated that programmable electronics could replace complex collections of dedicated logic circuits and dramatically simplify system design. Yet, even as the 4004 entered commercial production, another opportunity was already taking shape, one that would push microprocessor technology far beyond calculators and industrial controllers. This opportunity did not originate inside Intel's laboratories alone. Instead, it emerged from an ambitious effort to build a new kind of intelligent computer terminal. The project would eventually give rise to the Intel 8008, a processor that represented one of the most significant advances in early computing history. During the late 1960s, computer terminals were becoming increasingly important. Most organizations that owned computers relied on large mainframes or mini-computers located in centralized facilities. Users rarely interacted directly with these machines. Instead, they communicated through terminals that displayed information and accepted keyboard input. Many early terminals were little more than electronic typewriters, sending characters to a central computer and displaying responses. However, engineers began imagining smarter terminals capable of performing local processing, editing text, managing data, and reducing the workload placed on expensive central computers. One company pursuing this vision was Computer Terminal Corporation, later known as DataPoint. The company set out to develop an advanced programmable terminal, called the DataPoint 2200. Unlike conventional terminals, the DataPoint 2200 would contain its own processor, allowing it to execute many functions independently while communicating with larger computer systems when necessary. This approach promised faster performance, greater flexibility, and a more capable user experience. Originally, the DataPoint 2200's processor was not intended to be a microprocessor at all. The engineering team designed its central processing unit using numerous TTL integrated circuits spread across multiple circuit boards, following the standard design philosophy of the era. Recognizing the potential advantages of higher integration, Computer Terminal Corporation approached both Intel and Texas Instruments about implementing the processor on a single integrated circuit. The goal was ambitious: replace an entire processor assembly with one compact silicon chip. Intel accepted the challenge. Rather than inventing an entirely new architecture from scratch, Intel engineers worked from the instruction set and overall design concepts developed for the DataPoint project. Although the original DataPoint 2200 ultimately shipped using its own discrete logic processor because development schedules could not wait for Intel's chip to be completed, Intel continued refining the design independently. The result became the Intel 8008, introduced commercially in April 1972. The Intel 8008 represented a dramatic leap beyond the capabilities of the earlier Intel 404. The most obvious improvement was its move from a 4-bit architecture to an 8-bit architecture. Instead of processing only 4 bits of data at a time, the new processor handled 8-bit values in a single operation. This seemingly simple change doubled the processor's native data width and greatly expanded the complexity of calculations and operations it could perform efficiently. For software developers, the transition opened the door to much more capable programming techniques and more practical general-purpose computing. The expanded architecture also brought significantly greater memory capacity. Whereas the Intel 4004 had been designed with relatively modest memory requirements, suitable for calculators, the Intel 8008 could address up to 16 kilobytes of memory. Although tiny by modern standards, this represented a substantial increase at the time. Larger memory meant larger programs, more sophisticated operating routines, additional variables, and richer applications. Programmers gained room to create software that extended well beyond the narrow functions of embedded controllers. Intel also expanded the processor's instruction set, providing programmers with more powerful tools for manipulating data, controlling program flow, and interacting with memory. Additional instructions made it easier to implement increasingly sophisticated software algorithms. While programming the 8008 still required careful optimization because of limited resources, developers enjoyed far greater flexibility than had been possible on the earlier 4004. The processor itself contained approximately 3,500 transistors, a notable increase over the 2,300 transistors integrated into the Intel 404. Advances in semiconductor manufacturing allowed Intel's engineers to incorporate additional logic while maintaining acceptable manufacturing yields. Every extra transistor represented an opportunity to improve performance, expand functionality, or simplify programming. Although transistor counts remained tiny compared with modern processors containing tens of billions of transistors, the increase demonstrated how rapidly semiconductor technology was advancing during the early 1970s. Clock speed also improved modestly. The Intel 8008 operated at frequencies of up to approximately 800 kHz, depending on the specific implementation. While this increase alone did not dramatically transform performance, the combination of higher clock rates, wider data paths, expanded instructions, and improved architecture resulted in substantially greater computational capability. The processor could tackle problems that had been impractical or impossible for its predecessor. Despite these improvements, designing the Intel 8008 remained an extraordinary engineering challenge. Semiconductor fabrication technology was still in its infancy compared with later decades. Engineers carefully balanced transistor budgets, silicon, area, power consumption, manufacturing complexity, and reliability. Every design decision involved trade-offs. Adding new features consumed valuable chip space, while increasing complexity risked reducing manufacturing yields. Intel's engineers continually refined layouts and circuit designs to maximize capability without exceeding the practical limits of available manufacturing technology. The Intel 8008 also reflected an important shift in Intel's strategic outlook. The company no longer viewed microprocessors solely as controllers for specialized products. Instead, it increasingly recognized them as the foundation for entirely new classes of computing systems. The processor's architecture supported applications that extended into computer terminals, laboratory instruments, industrial automation, communication systems, and experimental microcomputers. Engineers around the world began exploring ways to build complete computer systems around a single microprocessor rather than relying on collections of discrete logic circuits. One of the Intel 8008's greatest contributions was demonstrating that microprocessors could evolve rapidly from specialized embedded controllers into practical computing engines. Although still limited by later standards, the processor possessed enough flexibility to encourage experimentation by researchers, engineers, universities, and electronics enthusiasts. Designers could now imagine compact computers that occupied a desktop rather than a room. The idea of affordable personal computing remained several years away, but the technological path leading toward it had become much clearer. The Intel 8008 was not without limitations. Programming remained complex. Memory, Capacity was still modest, and system designers often had to work around architectural constraints inherited from the data point design. Input and output operations required careful planning, and overall performance remained modest compared with contemporary mini-computers. Nevertheless, these shortcomings were overshadowed by the processor's remarkable potential. For many engineers, the Intel 8008 represented proof that the microprocessor could become the heart of increasingly sophisticated computing systems, rather than merely an electronic controller. Its influence extended beyond the products that immediately adopted it. The experience Intel gained while developing and manufacturing the 8008 directly informed future processor designs. Engineers learned valuable lessons about instruction sets, memory organization, semiconductor fabrication, software development, and system architecture. These lessons would shape the creation of even more powerful successors, including the Intel 8080, which would become one of the defining processors of the emerging personal computer industry. Looking back, the Intel 8008 stands as far more than simply the second chapter in Intel's microprocessor story. It represented a crucial bridge between the groundbreaking proof of concept established by the Intel 404 and the practical general-purpose processors that would soon ignite the personal computer revolution. By expanding from 4-bit to 8-bit computing, increasing transistor counts, enlarging memory capacity, and supporting more sophisticated software, the Intel 8008 transformed the microprocessor from a remarkable innovation into a technology with the power to reshape the entire future of computing. The Intel 4004 and the Intel 8008 are often compared because they were Intel's first two commercial microprocessors, introduced only months apart during one of the most transformative periods in computing history. At first glance, it might appear that the newer processor simply replaced the older one, rendering it obsolete almost immediately. Yet that interpretation overlooks the true relationship between these pioneering chips. The Intel 8008 was not the replacement for the Intel 4004 in a historical sense. Instead, it was the next evolutionary step in a technological journey that had only just begun. The 4004 proved that a complete programmable central processing unit could exist on a single silicon chip. The 8008 demonstrated how that revolutionary idea could be expanded into a far more capable computing platform. Together, they established the foundations upon which every later microprocessor would be built. The most obvious difference between the two processors was their architecture. The Intel 4004 was a 4-bit microprocessor, meaning it processed 4 bits of data at a time. This design reflected its original purpose as the controller for programmable calculators. Decimal arithmetic could be handled efficiently using 4-bit binary-coded decimal operations, making the processor well suited for its intended application. The Intel 8008, by contrast, introduced an 8-bit architecture. Doubling the processor's native data width allowed it to manipulate larger values in a single operation, simplifying software development while significantly increasing computational capability. Although moving from 4 bits to 8 bits might sound like a modest improvement, today it represented one of the most important architectural advances in early microprocessor history. The increase in transistor count illustrated how quickly semiconductor technology was advancing. The Intel 4004 contained approximately 2,300 transistors fabricated using silicon gate PMOS technology. Only a year later, the Intel 8008 increased that number to roughly 3,500 transistors. Every additional transistor gave engineers more freedom to implement richer instruction sets, additional internal logic, and expanded functionality. At a time when every transistor occupied valuable silicon area and directly affected manufacturing complexity, this increase reflected significant progress in both chip design and fabrication techniques. Clock speed alone tells only part of the performance story. The Intel 4004 operated at frequencies up to approximately 740 kHz, while the Intel 8008 reached about 800 kHz under suitable conditions. On paper, this difference appears relatively small. However, raw clock frequency does not fully capture processor capability. Because the Intel 8008 processed twice as much data per operation, supported a more powerful instruction set, and addressed substantially larger memory, it could perform many computing tasks far more efficiently than its predecessor. Performance depends not only on how fast a processor runs, but also on how much useful work it accomplishes during each cycle. Memory represented another area of dramatic improvement. The Intel 4004 was designed with relatively modest memory requirements, appropriate for calculators and embedded control systems. Its address space was sufficient for compact application programs, but limited the complexity of software developers could create. The Intel 8008 expanded addressable memory to as much as 16 kilobytes. Although this amount seems tiny today, it represented a substantial increase in 1972. Larger memory capacity enabled more sophisticated software, larger data structures, and increasingly ambitious computing applications. Developers could write longer programs, implement more advanced algorithms, and design systems approaching the capabilities of small computers rather than specialized controllers. Instruction sets further highlighted the evolution between the two processors. The Intel 404 included instructions carefully optimized for arithmetic operations, control logic, branching, and simple input-output functions, appropriate for programmable calculators and embedded devices. It was remarkably versatile within its design goals, but its capabilities naturally reflected the constraints of a first-generation microprocessor. The Intel 8008 expanded those capabilities considerably. Its richer instruction set provided programmers with greater flexibility when manipulating data, performing logical operations, controlling program execution, and managing memory. Although programming still required careful optimization, software developers enjoyed significantly more expressive power. The intended applications of the two processors also differed in important ways. The Intel 404 initially targeted programmable calculators through the BusyCom project, but engineers soon adapted it for industrial controllers, traffic management systems, medical instruments, vending machines, cash registers, laboratory equipment, and various embedded applications. Its compact size and programmability made it valuable wherever intelligent control was needed, within relatively limited computational requirements. The Intel 8008 broadened those possibilities considerably. While it could also serve embedded roles, its expanded architecture made it far more suitable for computer terminals, experimental microcomputers, communication systems, instrumentation, and general-purpose computing applications. The processor began shifting the industry's vision from intelligent controllers toward complete computers built around a single chip. From an engineering perspective, both processors demonstrated remarkable innovation, but in different ways. The Intel 404's greatest achievement lay in proving that an entire central processing unit could be successfully integrated onto one commercially manufactured silicon chip. Before its introduction, many engineers considered such integration extraordinarily difficult or even impractical. The 404 shattered that assumption. It established design methodologies, manufacturing techniques, testing procedures, and architectural concepts that became essential for future microprocessor development. The Intel 8008 built directly upon those engineering foundations. Rather than solving the question of whether a microprocessor could exist, Intel's engineers focused on expanding what a microprocessor could accomplish. The increased transistor budget enabled more sophisticated internal organization, while continued advances in semiconductor fabrication improved manufacturability and reliability. Every challenge overcome during the development of the 4004 informed decisions made during the creation of the 8008. In many respects, the second processor represented the maturation of ideas first proven by the first. Scalability became another crucial distinction. The Intel 4004 demonstrated the concept of programmable silicon, but its architecture naturally limited how far it could evolve within increasingly demanding computing environments. The Intel 8008 pointed toward a much more scalable future. Its wider data paths, expanded memory addressing, and richer programming model established architectural principles that would continue evolving through subsequent generations of Intel processors. These ideas eventually influenced processors capable of supporting operating systems, high-level programming languages, graphical interfaces, networking, and eventually modern personal computing. Manufacturing itself also improved during the brief interval separating the two chips. Intel continued refining silicon gate MOS technology, production methods, quality control procedures, and testing techniques. As engineers gained practical experience producing commercial microprocessors, yields improved and confidence in large-scale semiconductor integration increased. These manufacturing advances proved just as important as architectural improvements because they enabled increasingly complex chips to be produced economically and reliably. Perhaps the most important historical lesson is that the Intel 8008 did not diminish the significance of the Intel 4004. On the contrary, the newer processor reinforced the importance of its predecessor. Without the Intel 4004, there would have been no practical demonstration that a single-chip CPU was commercially viable. The design philosophies, engineering experience, and manufacturing knowledge developed during the 404 project made the 8008 possible. Every improvement incorporated into the newer processor rested upon lessons learned from the earlier one. History often celebrates the fastest, the largest, or the most powerful technologies, while overlooking the importance of foundational breakthroughs. Yet, technological revolutions rarely emerge fully formed. They develop through a sequence of innovations, each solving problems that allow the next generation to advance further. The Intel 404 represented the critical first step, the moment when the microprocessor became reality. The Intel 8008 represented the second step, showing that this new invention could grow beyond specialized embedded systems and begin approaching the capabilities required for genuine computing platforms. Together, these processors transformed the semiconductor industry. They changed how engineers thought about electronic design, replacing dedicated hardware logic with programmable architectures. They encouraged software-driven innovation, simplified hardware development, reduced manufacturing complexity, and inspired researchers worldwide to imagine computers that could become smaller, cheaper, and more accessible. The Intel 8008 did not erase the achievements of the Intel 4004. Instead, it extended them, proving that the microprocessor was not a single remarkable invention, but the beginning of an evolutionary process that would reshape technology for generations. As Intel continued refining its designs, the path toward truly practical personal computers became increasingly visible, setting the stage for the processors that would soon carry computing from research laboratories and corporate data centers onto the desks of millions of people around the world. The Intel 4004 proved that a complete central processing unit could fit onto a single silicon chip. The Intel 8008 demonstrated that the concept could be expanded into a more capable computing platform. Together, these pioneering microprocessors established the technological foundation for an entirely new industry. Yet the personal computer revolution did not begin the moment either chip reached the market. Revolutionary inventions rarely transform society overnight. Instead, they create opportunities that other innovators recognize, refine, and expand. During the years that followed, a remarkable chain of technological progress unfolded, with each breakthrough building directly upon those that came before. From the Intel 4004 and Intel 8008 emerged increasingly powerful processors, pioneering software companies, influential computer systems, and visionary entrepreneurs whose combined efforts would bring computing into homes, schools, and businesses around the world. The next major milestone arrived in 1974 with the introduction of the Intel 8080. Drawing upon the engineering experience gained from both the 4004 and the 8008, Intel designed a processor that significantly expanded performance, memory capacity, and programming flexibility. The Intel 8080 featured a more practical architecture for general-purpose computing, operated at higher speeds, and could address much larger amounts of memory. While the 8008 had demonstrated the promise of microprocessor-based computers, the 8080 provided the computing power necessary to make truly practical microcomputers a commercial reality. For engineers and electronics enthusiasts, the Intel 8080 represented an exciting opportunity. Building a computer no longer required designing an entire processor from hundreds of integrated circuits. Instead, one relatively inexpensive microprocessor could serve as the heart of a complete computer system. Designers needed memory, storage, input and output devices, and supporting electronics. But the greatest engineering challenge, the CPU itself, was now available as a single commercially manufactured component. This dramatically lowered both the cost and complexity of computer design. The breakthrough reached a much wider audience in 1975 with the introduction of the Altair 8800. Produced by Microinstrumentation and Telemetry Systems, commonly known as MITS, the Altair appeared on the cover of Popular Electronics magazine and immediately captured the imagination of hobbyists across the United States. Sold primarily as a kit, the machine invited users to assemble their own computer, install memory, connect peripheral devices, and write software for an affordable microprocessor-based system. Although primitive by modern standards, with front, panel switches, and blinking indicator lights replacing keyboards and monitors, the Altair demonstrated that personal computing was becoming practical for individuals rather than institutions. The Altair 8800's success extended beyond its hardware. It inspired a generation of programmers and entrepreneurs who recognized that affordable computers would require equally capable software. Among those paying close attention were two young friends, Bill Gates and Paul Allen. Fascinated by the possibilities created by the Altair, they realized that users would need a high-level programming language capable of making these new computers accessible to more people. Instead of forcing every owner to write programs directly in machine language, they envisioned software that would simplify development and encourage experimentation. Working with extraordinary determination, Gates and Allen developed a version of the basic programming language specifically for the Altair's Intel 8080 processor. Remarkably, much of the software was written before they had direct access to the actual hardware, relying instead on careful analysis and simulation. When Altair Basic successfully demonstrated that sophisticated software could run on an affordable microcomputer, it marked a pivotal moment in computing history. The project led directly to the creation of Microsoft, a company that would eventually become one of the most influential software developers in the world. The success of Microsoft Basic demonstrated another critical lesson. Inherited from the earliest microprocessors, Hardware alone could not transform computing. Powerful software was equally essential. Meanwhile, innovation was also accelerating elsewhere. On the west coast of the United States, a growing community of electronics enthusiasts gathered to exchange ideas about microprocessors and home-built computers. Among them was Steve Wozniak, an exceptionally talented engineer who believed that computers should be affordable, elegant, and easy to use. Inspired by the rapid advances in microprocessor technology, Wozniak designed a compact computer around the MOS Technology 6502 processor, another descendant of the broader microprocessor revolution made possible by the pioneering work of Intel and other semiconductor innovators. The resulting machine, introduced in 1976, became known as the Apple I. Unlike many earlier hobbyist systems, the Apple I arrived with much of its circuitry already assembled, making it considerably more accessible to users. Although buyers still needed to supply a keyboard, monitor, and power supply, the machine represented a significant step toward practical personal computing. Steve Jobs recognized its commercial potential, helping transform a small engineering project into the foundation of a new company called Apple Computer. Only 1 year later, Apple introduced the Apple II, one of the most successful early personal computers ever produced. With color graphics, an integrated keyboard, expandable architecture, and a design intended for ordinary consumers rather than electronics hobbyists, the Apple II demonstrated that personal computers could become useful household and business tools. Schools adopted them for education, small businesses used them for accounting and inventory management, and software. Developers created an expanding library of applications. The dream of bringing computing to millions of people was beginning to become reality. As the personal computer market expanded, Intel continued refining its own processor designs. Building upon lessons learned from the 8080, Intel introduced the 8086 in 1978, establishing the x86 instruction set architecture that would become one of the most influential computing standards in history. The 8086 and its close relative, the 8088, offered significantly improved performance while introducing architectural concepts that remain recognizable in modern processors decades later. The defining moment arrived in 1981 when IBM entered the personal computer market with the IBM Personal Computer, commonly known as the IBM PC. Rather than developing a proprietary processor, IBM selected Intel's 8088 as the machine's central processing unit. This decision had profound consequences. IBM's reputation gave businesses confidence in personal computing, while Intel's processor became the heart of one of the most successful computer platforms ever created. Microsoft, meanwhile, supplied the operating system that evolved into MS-DOS, strengthening the partnership between software and microprocessor technology. The success of the IBM PC established a technological ecosystem that expanded rapidly throughout the 1980s and beyond. Countless compatible computers adopted Intel-compatible processors and Microsoft software, creating a standardized platform that encouraged hardware innovation, software development, and widespread adoption. As Intel introduced increasingly advanced processors, including the 80286, 80386, 80486, Pentium, Pentium Pro, Pentium II, Pentium III, Pentium 4, Core, Core 2, Core i-Series, and many later generations, the original architectural principles pioneered during the company's earliest microprocessor projects continued evolving. Looking back across this remarkable chain of progress, the connections become unmistakable. The Intel 4004 demonstrated that an entire CPU could fit on a single silicon chip. The Intel 808 expanded that concept toward practical computing. The Intel 8080 delivered the performance needed for affordable microcomputers. The Altair 8800 inspired hobbyists and entrepreneurs. Microsoft BASIC made programming accessible. Bill Gates and Paul Allen founded a software company that would shape the industry for decades. Steve Wozniak and Steve Jobs helped popularize personal computers through Apple. IBM legitimized the personal computer for businesses around the world. Intel's x86 architecture evolved into one of the dominant processor families in computing history. None of these milestones existed in isolation. Each depended upon the engineering achievements that came before it. Every generation of processors benefited from advances in semiconductor manufacturing, architectural innovation, software development, and system design accumulated over previous years. The path from the Intel 4004 to today's computers was not a series of disconnected inventions, but a continuous chain of innovation, in which every link strengthened the next. The personal computer revolution was therefore not the accomplishment of a single company, one engineer, or one product. It was the result of decades of collaboration, competition, and relentless improvement across the semiconductor and software industries. Yet, at the very beginning of that extraordinary journey stood two tiny microprocessors introduced in 1971 and 1972. Their transistor counts were measured in mere thousands, their clock speeds in kilohertz, and their memory capacities in only a few kilobytes. Despite these humble specifications, they ignited a technological transformation whose influence continues to shape every computer, every smartphone, every cloud server, and every artificial intelligence system operating in the modern world. The story of the Intel 4004 and the Intel 8008 does not end in the early 1970s. In many ways, those pioneering chips represent the opening chapter of a technological journey that continues more than half a century later. Every generation of processors introduced since then has built upon the same fundamental idea first demonstrated by Intel's earliest microprocessors: integrate increasing amounts of computing power into increasingly smaller pieces of silicon while improving speed, efficiency, reliability, and programmability. Although modern processors differ enormously from their early ancestors in complexity and capability, the basic concept remains remarkably familiar. A programmable central processing unit executes instructions, manipulates data, communicates with memory, and coordinates every function of a computing system. The remarkable difference lies in how far semiconductor engineering has advanced. Consider the enormous gap between the Intel 4004 and a modern desktop processor. The 4004 contained approximately 2,300 transistors. Today's high-performance processors integrate tens of billions of transistors onto a single package, representing an increase of several million times in component density. Clock frequencies have risen from hundreds of kilohertz to several gigahertz, allowing billions of clock cycles every second. Instead of executing roughly 92,000 instructions per second, modern processors can perform billions of operations each second while simultaneously running multiple software applications, managing complex operating systems, and communicating with graphics processors, storage devices, and networks around the world. One of the clearest examples of this evolution can be seen in Intel's own processor families. Following decades of continuous innovation through the 8080, 8086, Pentium, and many other generations, Intel eventually introduced the Intel Core series. These processors became the foundation of countless desktop computers, laptops, workstations, and servers used throughout homes, schools, businesses, and research institutions worldwide. Modern Intel Core processors contain multiple processing cores capable of executing numerous instruction streams simultaneously. Sophisticated cache hierarchies reduce memory latency, advanced branch prediction improves execution efficiency, and specialized instruction sets accelerate multimedia processing, encryption, scientific computation, and artificial intelligence workloads. Every one of these sophisticated capabilities traces its conceptual heritage back to the early microprocessor architecture pioneered by the Intel 4004 and expanded by the Intel 8008. Competition has played an equally important role in advancing processor technology. AMD, founded only 1 year after Intel, evolved from a second-source semiconductor manufacturer into one of the world's leading processor designers. Its Ryzen family has become one of the most successful modern CPU architectures, offering exceptional performance for gaming, content creation, engineering, and professional computing. Through decades of competition between Intel and AMD, consumers have benefited from rapid improvements in performance, power efficiency, manufacturing technology, and architectural innovation. This competitive environment has accelerated progress far, beyond what either company could likely have achieved alone. Another remarkable chapter in processor evolution emerged through Apple. During its early years, Apple computers relied on processors developed by other companies, including the Motorola 68000 family, PowerPC architectures, and eventually Intel processors. In 2020, however, Apple began transitioning its Macintosh computers to Apple Silicon, a family of processors designed in-house using ARM architecture. The Apple M series demonstrated the tremendous advantages of tightly integrating central processing, graphics processing, memory management, and specialized accelerators into highly efficient systems on a chip. Although architecturally different from Intel's x86 lineage, Apple Silicon reflects the same long-term engineering philosophy first established by the earliest microprocessors: integrate more computing capability into increasingly compact, efficient silicon. The influence of early microprocessors extends far beyond traditional personal computers. Modern graphics processing units, or GPUs, have evolved into extraordinarily powerful parallel computing engines capable of executing thousands of operations simultaneously. Originally developed to accelerate computer graphics, GPUs now play central roles in scientific computing, engineering simulation, cryptocurrency, video processing, and artificial intelligence. Companies such as NVIDIA, AMD, and Intel continue advancing GPU technology, enabling applications that would have seemed almost unimaginable during the era of the Intel 404. Despite their architectural differences, these processors remain descendants of the same semiconductor revolution that began when engineers first demonstrated programmable computing on a single chip. Cloud computing provides another powerful example of the enduring legacy established by those early microprocessors. Instead of relying solely on local computers, businesses and individuals increasingly access computing resources hosted inside massive data centers distributed across the globe. Thousands upon thousands of processors operate continuously inside these facilities, supporting online banking, video streaming, social media platforms, scientific research, enterprise software, and countless internet services. Although users rarely see these machines, they depend on processors that represent decades of continuous architectural evolution from the earliest commercial microprocessors. Artificial intelligence has become one of the defining technologies of the 21st century, and once again, the microprocessor stands at its foundation. Modern AI systems require extraordinary computational resources to train and operate increasingly sophisticated machine learning models. Specialized AI accelerators, tensor processing units, neural processing units, and advanced GPUs now complement traditional CPUs in performing these demanding calculations. Personal computers increasingly include dedicated AI hardware capable of accelerating language models, image generation, speech recognition, and intelligent assistance while reducing power consumption and improving responsiveness. The emergence of AI PCs illustrates how processor technology continues evolving. Rather than serving merely as general-purpose computing devices, modern personal computers increasingly incorporate specialized hardware designed specifically for artificial intelligence workloads. Dedicated neural processing units can execute billions of mathematical operations with remarkable energy efficiency, enabling real-time translation, image enhancement, background noise removal, content generation, and intelligent productivity features directly on local devices. These capabilities would have seemed almost magical to engineers working on the Intel 4004, yet they represent the natural continuation of the same engineering principles established more than 50 years ago. Perhaps the most astonishing transformation lies in the devices carried by billions of people every day. Modern smartphones possess computational capabilities that vastly exceed those of the largest supercomputers from the early 1970s. A typical smartphone integrates multi-core CPUs, powerful GPUs, AI accelerators, image processors, wireless communication systems, security hardware, multimedia engines, and enormous memory capacity into a package small enough to fit comfortably inside a pocket. Users routinely navigate global positioning systems, capture high-resolution video, conduct video conferences, edit photographs, access cloud services, and interact with artificial intelligence using devices that operate for hours on battery power alone. Such extraordinary integration reflects the long-term trajectory first demonstrated by the Intel 4004, place increasingly sophisticated computing functions onto silicon while continuously reducing size, cost, and power consumption. The semiconductor manufacturing industry has undergone an equally remarkable transformation. Early microprocessors were fabricated using processes measured in micrometers. Today, leading-edge manufacturing technologies measure critical features in only a few nanometers, allowing billions of transistors to occupy areas smaller than a postage stamp. Advanced lithography systems, automated design software, sophisticated packaging techniques, and precision manufacturing enable semiconductor complexity that early engineers could scarcely imagine. Yet every new manufacturing generation continues pursuing the same objective that motivated Intel's pioneers in the early 1970s: integrate more capability into less space while improving performance and reliability. Looking across more than 5 decades of innovation, one theme becomes unmistakably clear. Modern processors did not emerge through a single revolutionary leap. They evolved through continuous engineering progress, with each generation building upon the discoveries, successes, and lessons of those that came before. The Intel 4004 introduced the world's first commercial microprocessor. The Intel 8008 expanded its capabilities toward general-purpose computing. Successive generations refined architecture, increased transistor counts, improved manufacturing techniques, expanded memory, enhanced software compatibility, and introduced entirely new forms of specialized computation. Today, whether someone is editing a video on an Intel Core workstation, compiling software on an AMD Ryzen desktop, designing music on an Apple Silicon Mac, training artificial intelligence models using powerful GPUs, or accessing cloud services hosted inside enormous data centers, they are participating in a technological legacy that began with 2 remarkably modest pieces of silicon introduced in 1971 and 1972. Their specifications have long since been surpassed, but their significance has only grown with time. The Intel 4004 and Intel 8008 did more than launch the age of the microprocessor. They established the conceptual foundation upon which every modern computing platform continues to evolve, from calculators to cloud computing, from embedded controllers to AI-powered personal computers. Their legacy lives on in every instruction executed, every calculation completed, and every technological breakthrough still waiting to be discovered. Behind every great technological revolution stand individuals whose ideas, determination, and engineering skill transform ambitious concepts into reality. The story of the Intel 404 and the Intel 808 is often told through specifications, product launches, and semiconductor breakthroughs. But at its heart, it is a story about people. 4 engineers in particular, Federico Faggin, Ted Hoff, Stanley Mazor, and Masatoshi Shima, played indispensable roles in creating the world's first commercial microprocessor and shaping the future of modern computing. Each brought a different set of talents to the project, and together they demonstrated how collaboration across disciplines and continents could produce innovations that changed the world. Among these pioneers, Federico Faggin is widely recognized as one of the central figures responsible for turning the microprocessor from an ambitious concept into a working commercial product. Born in Vicenza, Italy, in 1941, Faggin displayed exceptional technical ability from an early age. After studying physics and electronics, he began working in the semiconductor industry during a period when integrated circuit technology was advancing at an extraordinary pace. His career eventually brought him to Fairchild Semiconductor in California, where he helped develop silicon gate MOS technology, a manufacturing breakthrough that dramatically improved the performance and density of integrated circuits. Silicon gate technology proved to be one of the essential ingredients that made the Intel 404 possible. Earlier manufacturing methods placed severe limitations on transistor density and performance, making it extremely difficult to integrate an entire processor onto one chip. Faggin's expertise allowed Intel to take advantage of this advanced fabrication process, enabling smaller, faster, and more reliable transistors than had previously been practical. When he joined Intel in 1970, the company assigned him to lead the implementation of the revolutionary processor architecture proposed for the Busicom calculator project. Faggin's responsibilities extended far beyond simply drawing circuit layouts. He developed the detailed chip design, transistor-level implementation, timing architecture, testing methodology, manufacturing processes, and project management required to transform a theoretical design into a commercially manufacturable semiconductor device. Working under intense technical and commercial pressure, he solved countless engineering problems that had never before been encountered in the production of a single-chip CPU. Many historians of computing credit Faggin not only with designing the Intel 4004 itself, but also with establishing practical methodologies that influenced the development of future generations of microprocessors. His contributions did not end with the 404. Faggin continued playing important roles in the development of later Intel processors, including the Intel 8008 and the Intel 8080. After leaving Intel, he co-founded Zilog, where he led the creation of the Z80 microprocessor. Introduced in 1976, the Z80 became one of the most successful microprocessors of its era, powering home computers, business systems, video game consoles, industrial equipment, and countless embedded devices. Throughout his career, Faggin received numerous honors recognizing his influence on semiconductor technology, including the National Medal of Technology and Innovation, one of the United States' highest distinctions for technological achievement. His work helped define the architecture and manufacturing techniques that continue shaping processor design today. Ted Hoff approached the challenge from a different perspective. Rather than focusing primarily on semiconductor fabrication, Hoff excelled at computer architecture and systems thinking. Born in 1937, he earned advanced degrees in electrical engineering before joining Intel as one of its early employees. When Intel received Busicom's calculator design, Hoff carefully analyzed the proposed collection of specialized integrated circuits. Instead of accepting the existing plan, he questioned its underlying assumptions. Why should every calculator function require its own dedicated chip? Could a programmable processor perform those same functions more efficiently? This question became the foundation of the microprocessor revolution. Hoff proposed replacing numerous custom logic circuits with a single programmable central processing unit, capable of executing software instructions, a profound shift in engineering philosophy. Rather than designing hardware for every individual task, manufacturers could increasingly rely on software to define system behavior. Hoff's architectural vision transformed the Busicom project from an advanced calculator into the birthplace of the commercial microprocessor. Although others carried the concept into physical silicon, Hoff's contribution lay in recognizing that programmability itself offered the greatest long-term value. His architectural insight extended far beyond calculators, anticipating a future in which programmable processors would become universal components across countless industries. In recognition of his groundbreaking work, Hoff received numerous awards throughout his career, including induction into the National Inventors Hall of Fame. His architectural thinking continues influencing processor design decades after the introduction of the Intel 4004. Working closely alongside Hoff was Stanley Mazor, another essential member of Intel's pioneering engineering team. Born in Chicago in 1941, Mazor developed expertise in computer architecture and software during the formative years of the semiconductor industry. At Intel, he collaborated extensively with Hoff in refining the processor's instruction set, programming model, and overall system architecture. While Hoff provided the initial conceptual framework, Mazor helped translate those ideas into a coherent architecture that programmers could use effectively. Designing an instruction set involved balancing many competing priorities. The processor needed enough flexibility to perform a wide range of operations while remaining sufficiently compact to fit within the limited transistor budget available at the time. Every instruction occupied valuable hardware resources, yet every omission risked limiting the processor's usefulness. Mazor's work helped produce an elegant and practical instruction set that contributed significantly to the commercial success of the Intel 4004. Beyond his engineering contributions, Mazor also became an influential educator and advocate for semiconductor technology. Throughout his career, he taught, lectured, and mentored new generations of engineers, sharing the lessons learned during the earliest days of the microprocessor revolution. His ability to explain complex architectural concepts made him an important ambassador for the history of computing and the significance of early semiconductor innovation. No account of the Intel 4004 would be complete without recognizing Masatoshi Shima. Born in Japan in 1943, Shima joined Busicom as an engineer responsible for developing advanced calculator systems. Unlike Intel's engineers, who approached the project primarily from the perspective of semiconductor technology, Shima possessed detailed knowledge of the calculator's functional requirements and commercial objectives. His close collaboration with Intel ensured that the emerging processor architecture remained practical for real-world applications. Shima did far more than simply communicate design requirements. He worked directly with Intel's engineering team throughout the development process, contributing technical expertise, reviewing architectural decisions, and helping solve implementation challenges. His understanding of both hardware and system behavior made him a valuable partner whose contributions significantly strengthened the final product. The Intel 404 emerged not from isolated engineering efforts, but from continuous collaboration between Busicom and Intel, with Shima serving as one of the most important links connecting the two organizations. After the completion of the Intel 4004, Shima continued collaborating with Intel during the development of subsequent processors, including the Intel 8080. Later, he joined Federico Faggin at Zlog, where he contributed to the creation of the highly successful Z80 microprocessor. Like the other pioneers, Shima's influence extended well beyond the first commercial microprocessor, shaping several generations of semiconductor innovation. What makes the achievements of these four engineers especially remarkable is that none of them worked alone. The creation of the Intel 404 required expertise in architecture, semiconductor, physics, circuit design, manufacturing, testing, programming, project management, and product engineering. Every breakthrough depended upon effective collaboration among specialists possessing different skills and perspectives. Their success illustrates one of the defining characteristics of modern engineering. Transformative innovations rarely emerge from isolated genius alone. They arise through teamwork, shared knowledge, constructive debate, and relentless determination to solve problems previously considered impossible. The recognition these pioneers eventually received reflects the enormous impact of their work. Their names appear in engineering halls of fame, prestigious award ceremonies, academic publications, and historical accounts of computing. Universities teach their innovations as foundational milestones in computer architecture. Museums display the Intel 4004 as one of the most significant technological artifacts of the 20th century. Historians consistently rank the invention of the commercial microprocessor among the defining engineering achievements of the modern era. Perhaps the greatest measure of their legacy, however, cannot be found in awards or honors. It exists instead in the billions of processors operating throughout the world today. Every laptop used by a student, every smartphone carried in a pocket, every cloud server supporting online communication, every industrial robot assembling automobiles, every satellite orbiting Earth, every medical imaging system assisting physicians, and every artificial intelligence model running on advanced processors owes something to the work begun by these pioneers more than 50 years ago. Federico Faggin, Ted Hoff, Stanley Mazor, and Masatoshi Shima did not simply design early semiconductor devices. They changed the direction of technological history. Their innovations transformed the microprocessor from an ambitious engineering experiment into the foundation of the digital age, proving that a tiny piece of silicon could become one of humanity's most powerful tools for invention, discovery, communication, and progress. More than half a century has passed since Intel introduced the 4004 in 1971 and the 8008 in 1972, yet their influence remains woven into nearly every aspect of modern life. What began as two modest silicon chips containing only a few thousand transistors ultimately reshaped the trajectory of technology, industry, science, and society. Their specifications have long been eclipsed by generations of increasingly powerful processors, but their historical significance has only grown with time. Looking back across the decades, it becomes clear that these pioneering microprocessors did far more than introduce a new category of semiconductor device. They fundamentally changed how engineers thought about computing and established the technological foundation for the digital world we now take for granted. The Intel 404 deserves its place in history because it accomplished something no commercial product had achieved before. It proved that the essential functions of a programmable central processing unit could be integrated onto a single silicon chip and manufactured as a reliable commercial product. Prior to its introduction, processors were assembled from numerous integrated circuits spread across multiple circuit boards. Designing a computer required managing hundreds of individual components, complex wiring, and extensive hardware engineering. The 4004 condensed that complexity into one integrated circuit, demonstrating that computing power could become dramatically smaller, simpler, and more accessible. Its technical specifications now appear remarkably modest. A 4-bit architecture, approximately 2,300 transistors, a maximum clock frequency of around 740 kilohertz, and roughly 92,000 instructions per second seem insignificant when compared with modern processors, containing tens of billions of transistors operating at gigahertz frequencies. Yet measuring the Intel 404 solely by modern performance standards misses the true importance of the achievement. Innovation should always be understood within the context of its own era. In 1971, integrating an entire programmable CPU onto one commercially viable chip represented an engineering breakthrough of extraordinary significance. It transformed a theoretical possibility into practical reality. The Intel 8008 built directly upon that foundation while expanding the possibilities of microprocessor design. By moving from a 4-bit architecture to an 8-bit architecture, increasing transistor count to approximately 3,500, expanding addressable memory to as much as 16 kilobytes, and providing a richer instruction set, Intel demonstrated that the microprocessor could evolve beyond specialized calculator applications into the heart of increasingly capable computing systems. The 8008 did not replace the historical importance of the 404. Instead, it validated and extended the original concept, proving that programmable processors could continue advancing rapidly as semiconductor technology improved. This progression illustrates one of the defining characteristics of engineering. Revolutionary technologies rarely emerge fully developed. Instead, they evolve through continuous refinement, with each generation solving limitations revealed by its predecessor. The Intel 4004 answered the question of whether a complete CPU could fit on one chip. The Intel 8008 answered the next question by demonstrating how that architecture could become more practical for broader computing applications. Later processors, such as the Intel 8080, 8086, and the generations that followed, continued this pattern, steadily increasing performance, expanding capabilities, and opening entirely new possibilities for software developers and system designers. The impact of these innovations extended far beyond Intel itself. Affordable microprocessors enabled the emergence of hobbyist computers, which inspired entrepreneurs to imagine personal computing as a mass-market industry rather than a specialized research tool. Software companies recognized opportunities to develop programming languages, operating systems, and applications for these new machines. Educational institutions adopted computers for teaching and research. Businesses began integrating computing into daily operations. Families eventually welcomed personal computers into their homes, transforming how people learned, communicated, created, and worked. The chain of innovation that followed remains one of the most remarkable examples of cumulative technological progress in modern history. The Intel 8080 powered early microcomputers that demonstrated the commercial potential of affordable computing. The Altair 8800 inspired a new generation of software developers, including Bill Gates and Paul Allen, whose work on Microsoft BASIC led to the creation of Microsoft. Steve Wozniak's engineering brilliance and Steve Jobs' entrepreneurial vision helped establish Apple as a leading force in personal computing. IBM's decision to build its personal computer around an Intel processor accelerated business adoption worldwide. Intel's x86 architecture evolved through countless generations, becoming one of the dominant processor families in computing history. Each milestone depended upon the engineering achievements that had come before. As semiconductor technology advanced, processors expanded beyond desktop computers into nearly every aspect of modern civilization. Microcontrollers now regulate automobile engines, manage household appliances, monitor industrial equipment, control aircraft systems, operate satellites, and power medical devices that save lives. Every day, smartphones place extraordinary computing power into the hands of billions of people, enabling global communication, navigation, photography, banking, education, and entertainment through devices that fit comfortably inside a pocket. Massive cloud data centers support internet services connecting individuals and organizations across every continent. Artificial intelligence systems capable of language understanding, image recognition, scientific research, and complex decision-making depend upon processors whose conceptual lineage extends directly back to the earliest microprocessors. Perhaps the most remarkable aspect of this history is the continuity of its underlying principles. Although modern processors differ enormously in complexity from the Intel 4004 and Intel 8008, they still perform the same fundamental tasks. They fetch instructions, decode operations, manipulate data, communicate with memory, and coordinate every aspect of a computing system. Advances in semiconductor manufacturing, architectural design, parallel processing, energy efficiency, and specialized accelerators have dramatically expanded what processors can accomplish. But the essential concept introduced by those pioneering chips remains recognizable more than 50 years later. The engineers responsible for these breakthroughs also leave an enduring legacy. Federico Faggin transformed revolutionary architectural ideas into manufacturable silicon using innovative silicon gate technology. Ted Hoff envisioned replacing numerous specialized circuits with a single programmable processor, fundamentally redefining computer architecture. Stanley Mazor refined the instruction set, an architectural framework that allowed programmers to harness the processor's capabilities effectively. Masatoshi Shima's collaboration ensured that practical system requirements guided the engineering process from concept to completion. Their combined expertise illustrates how great technological revolutions emerge through collaboration among individuals with complementary skills rather than through isolated invention alone. Their achievements also highlight the importance of persistence in engineering. None of the challenges they faced had established solutions. They confronted manufacturing limitations, transistor budgets, architectural uncertainties, testing difficulties, and commercial pressures while attempting something the industry had never accomplished before. Success required imagination, technical excellence, disciplined experimentation, and the willingness to pursue ideas that many considered unrealistic. The resulting microprocessors became not merely successful products, but symbols of what determined engineers can accomplish when they challenge conventional assumptions. Today, the world stands at the threshold of another remarkable era in computing. Artificial intelligence is reshaping industries ranging from medicine and manufacturing to education and scientific research. Cloud computing connects billions of devices through global networks. Quantum computing promises entirely new approaches to solving certain classes of problems. Advanced robotics, autonomous vehicles, augmented reality, and space exploration continue pushing the boundaries of technological possibility. Every one of these fields depends upon the relentless progress of semiconductor engineering that began with the earliest commercial microprocessors. It is easy to become captivated by the immense power of modern processors and overlook the tiny chips that started the journey. Yet, history reminds us that every technological revolution begins with a first step. The Intel 4004 was that first decisive step into the age of the commercial microprocessor. The Intel 8008 showed that the path ahead extended far beyond calculators toward general-purpose computing. Together, they transformed a bold engineering experiment into the foundation of the personal computer revolution and ultimately the digital civilization that now surrounds us. From a few thousand transistors etched onto tiny pieces of silicon emerged a future filled with personal computers, global communication networks, smartphones, cloud infrastructure, artificial intelligence, and technologies that continue expanding the limits of human knowledge and creativity. Their creators could scarcely have imagined the full extent of their influence, yet their work demonstrated one timeless truth about innovation. Sometimes the smallest inventions create the largest changes. Two tiny microprocessors, introduced just 1 year apart, did more than advanced electronics. They changed the future of computing forever, proving that extraordinary revolutions can begin with something small enough to rest on the tip of a finger, yet powerful enough to reshape the course of human history.